What's up, everybody? Welcome to the first lecture of Trig. Today we're going to be talking about really just that first PowerPoint that's up on Blackboard. To start off with, let's talk about angles. We generally know, just from our previous experiences with high school and all, what an angle is, right? We've got these two rays, they're connected at a single point, and we want to be able to measure the separation between their ends. Well, that measurement is what we call an angle, right? So we have an initial side and a terminal side. Both of these rays are connected together at a single point, which we call a vertex. And we use this measurement of angle to measure how separated they are, how far apart the opposite ends are. Okay, pretty straightforward. From there, it's not enough just to talk about angles, right? We need a way of orienting ourselves. So we have this other idea of standard position, which is exactly that. It's the idea of how are we going to orient these shapes, these triangles, these circles, etc., so that we can kind of all agree on what it is we're measuring, what it is we're talking about. To get that orientation, to kind of understand and have an agreement on that orientation, we use what's called the standard position. And all that standard position does is it says, let me take and put my initial side along the positive x-axis. Let me then put the vertex at the origin. And let me put the terminal side wherever it might land. From there, we're going to measure the angle the exact same way we had before. Having said this, I want to point something out. Notice that if we change the length of the initial side, and we thought of it as the terminal side as being the initial side just moved forward and backwards, right? So what I'm saying is, if we've pictured this sort of scenario, we start off with the initial side, we set the length of it, we say, all right, rotate, 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 until we get to the terminal point, the terminal side. All right, cool, stop here. Fixing this angle, or fixing this length, I mean to say, if we were to rotate this 360 degrees, we'd trace out a perfect circle, right? That's a perfect circle. Yeah, that's a perfect circle. Quotation marks. So with this observation in mind, let's just call that length the radius, just because it's convenient. Okay, so we're going to call this length the radius. And we're going to say, with this radius in mind, if I were to follow the end of our initial side, put a point on it, and trace that point all the way up until we reach wherever the terminal side is supposed to stop at, we'd get a nice little arc. It would kind of look like just a sliver of a pie, right? So we have this arc, the initial side, and the terminal side. The terminal side has the same length as the initial side. We call this arc an arc segment. Go figure. And it has a length that we call the arc length. And if we wanted to measure whatever this angle is, assuming we knew the length of the arc segment, we can measure that angle in what's called radians. And what that looks like is to say, all right, cool, let's take the arc length and divide it by the radius. That's all it is. And that's going to give us the angle, the measurement of angles in terms of radians. Again, pretty straightforward. Having said that, some observations we can make now. If we don't rotate this at all, well, we're at 0 radians because there would be no arc segment, right? So 0 divided by the radius, 0. Dope. If we were to go halfway around to here, here, let me actually clear this up a little bit. So if we were to now go halfway around, well, that's half a circle. We know a circle has a circumference of 2 pi, or 2 pi times the radius, I need to say. Well, half a circle then is going to have a circumference of just pi times the radius. All right, so that means the segment from here halfway around is just going to be pi r. So that means the arc, or I mean the angle from initial all the way around is just going to be pi. Dope. From here, we might be able to figure out what the rest of it's going to be. Up top, the angle will be pi over 2. And down below, it's going to be 3 pi over 2. Notice if we go all the way around, though, we've traced out 2 pi. 2 pi radians. So what this is telling us, and I know I didn't quite explain all of this 110%, just go with me here. What this is all telling us put together is that if we were to measure, if we were to be given a triangle and asked, give me its radians, or give me its angle in radians, we could say, all right, cool, give it to me in standard position. All right, I'll give it to you in standard position. Based on where its terminal side ends, we should be able to guess at what range the radians might fall in. What I'm saying is, if the terminal side ends in our first quadrant, then our angle measured in radians will be between 0 and pi over 2. In the second quadrant, it's going to be between pi over 2 and pi. If the terminal side is somewhere in our third quadrant, then the angle is going to be between pi and 3 pi over 2. And finally, if our terminal side ends up somewhere in the fourth quadrant, well, we know that the angle is going to be between 3 pi over 2 and 2 pi. Alright. What is all of this? What the hell did I just say? What did I do? Because this kind of sucked, right? What I said, what I started off with was to say, let's imagine, if we can, we start off with a single line. Now let's take one end of that line and fix it at our origin. Now let's fix the little length of that line. Okay, cool. Now, let's rotate that line about the origin, tracing out the opposite end. So if we're fixing it here, we're going to trace it out wherever that other end is. We're going to notice that, well, that trace gives us part of an arc, part of a circle. And we know that that arc, the length of it, that arc segment, it's going to be related to the angle. And it's going to be related to the angle through what are known as radians. So we're measuring the angle in radians. Moreover, because of this, we can also say, hey, dope, I don't need to really know right away what the angle is. If you can put it up in standard position, I can already give you an idea of what the angle is going to be, just because of where the terminal end lands. In the meantime, all right, cool. So I know where the terminal end ends. I have an idea of what the angle is going to be. Let me get the angle now. All right, well, what's the arc length? What's that arc that connects the initial end to the terminal end, wherever it might be? If I know that length, then I can for sure tell you what the angle is going to be. And I can use this observation to check it. That's really the gist of what these first couple slides are getting at. Having said that, let's move on. Before we go any further, I want to go over some quick vocab. To start off with, right angles. A right angle is formed when the two sides that we put together to make these triangles, when the two sides are separated by an angle of 90 degrees or pi over 2 radians. From there, if two sides are, if two triangles, or two angles, I should say, if two angles are complementary, what we're saying is that when we add those two angles together, they add up to 90 degrees or pi over 2. So we can imagine we have two different triangles. One has an angle of alpha. The other has an angle of beta. When we add them together, if they add up to 90 degrees or pi over 2 radians, we're going to say that the two angles are complementary. From there, supplementary angles, same idea, except instead of adding up to 90 or pi over 2, they're going to add up to 180 or just pi radians. So we can think again of two different triangles, one with a measure of, an angular measure of alpha, the other of beta. If we were to put these two triangles together, we'd see them form a straight line with this sort of line in the middle separating. Cool. Looking at this though, this hints at something, right? It hints at a relationship between degrees and radians. So what about that? What's the relationship between the two? Let's look at that. So to answer this question of what's the relationship between degrees and radians, let's think back to the circle really quickly. A few minutes ago I had said that our axes lie along particular radian angles, right? That if our terminal end ended here, the measurement in radians was either going to be 0 radians or 2 pi radians, depending on how we moved that terminal end, right? If we just left it sitting there, it'd be 0 radians. If we moved it all the way around and back 2, then it would be 2 pi radians. Okay. And I said, if we took that terminal end and we moved it up, well, that would be a measure of pi over 2 radians, right? That's what that angular measurement would be. That's all we separated the 2 by, an angle of pi over 2 radians. And we know that's 90 degrees. We know that these two axes are separated by 90 degrees, right? Yeah. And if we rotated it again, this time so that the terminal side is lying along the negative x-axis, well, that forms a line, and we know a line has an angle of 180 degrees. And we had already said that it's just pi radians. And we do it again along the negative y-axis now. This is 270 degrees, or 3 pi over 2 radians. And like I said, if we move all the way around, we know we've moved 360 degrees, or 2 pi radians. Now notice something. We started off at 0 radians. Then we moved up, we rotated up, pi over 2 radians to 90 degrees, right? Same measurement, pi over 2 radians, 90 degrees. Kind of like feet to inches, inches to miles, meters to centimeters, whatever, right? That's really what these two comparisons are. And then if we rotated another pi over 2 radians to pi radians, it's 180 degrees. That's just like adding 90 degrees, 90 degrees. Okay, I think I see a pattern, maybe. So we do it again. Another pi over 2 radians, and we add another 90 degrees. Okay, I'm pretty sure I see the pattern now. But just to be sure, we do it one last time. We rotate all the way around, pi over 2, another pi over 2, another pi over 2, all the way up until we get to 2 pi radians. And it's 360 degrees. So yeah, there's definitely a relationship here, right? It looks like pi over 2 radians is equal to 90 degrees. In fact, that's true. It is. Okay. That's convenient. What if I don't know? What if I'm not at a nice angle? What if I'm at like pi over 4? What is that in degrees? Well, let's use what we know. We know that 180 degrees is equal to pi radians. Okay? And there's a linear relationship between radians and degrees. So we can convert directly between the two of them just like we would if it was feet to inches, or inches to miles, or miles to meters. Same exact idea. It's just a conversion. All we're doing is we're going to say, using what we know, we want to move from radians to degrees, or degrees to radians. And we know 180 degrees is equal to pi radians. Okay, so this gives me a thought. If I'm given an angle in degrees, and I want to know what it is in radians, all I have to do is multiply that angle in degrees by pi radians over 180 degrees. And this is going to be equal to our angle in radians. And if we want to go the opposite direction, we just flip that fraction. If we want to go in the opposite direction, we would say our angle in radians times 180 degrees over pi is equal to our angle in degrees. All right. So let's start putting some of this together. Let's look at an example now. I'll be right back with that. So, this first example, we're given a triangle. We're given just our base and our terminal end, right? Where the two ends are separated by an angle of 120 degrees. Okay. I want to know what that is in radians. So, we know the angle in degrees is equal to 120 degrees. To find it in radians, we're going to use the formula that we just talked about, our angle in degrees times pi over 180. Okay. So we just plug in 120 degrees in now. Cool. 120 times pi over 180. Well, we can rearrange our terms and reduce our fraction. So let's do that. Over 180 times pi. We can instantly see that we can divide by 0, or by 10. Can never divide by 0. Nick said I just said 0. I meant to say 10. We can see we can divide the numerator and the denominator both by 10. Just X out that 0, right? Okay. So if we do that, we're going to get 12 over 18 times pi. We can reduce this fraction even further to 4 over 6 or to 2 over 3. Over 3 pi. And that's it. We're done. Game over. (120 degrees in radians is 2 over 3 pi radians. Cool. All right. Pretty quick. Let's look at another example. So in this second example, I decided to be a little extra. Sorry, guys. What we're looking for in the second example is going to be the angle separating these two lines, the initial side and the terminal side. We're looking for this angle in degrees. And to find it, what we're given is that these two sides, they sit inside of a partial circle. And that circle is going to be a radius of 2. And that arc length of the partial circle is going to be 14 over 6 times pi. What? How? Why? Who comes up with these problems? I did. I came up with it. Sorry, guys. So how are we going to do this? Well, the first thing we want to do is we want to go back to what we know, right? We don't want to invent new math. We want to go back to those fundamental building blocks that we started the lecture off with. Good thing, because it's day one of the lecture. And if we had to invent math for this class, oh man, we'd all be in trouble, right? Okay, so we want to start off with that very first formula we saw. The way radians are calculated. And what that formula said is that our angle in radians is equal to the arc length of our partial circle divided by the radius of that circle. Okay, well, we know the arc length and we know the radius. So we can find the angle in radians. And from there, we know that we can find it in degrees. So let's do that. Plugging everything in, we've got 14 over 6 times pi divided by 2. All right, well, we can break these up into two different fractions now, so let's do that. That's 1/2 times 14 over 6 times pi. We can rewrite these fractions. We can move this 14 over to the 1/2. Over 2 times 1 over 6 times pi. Well, this conveniently reduces for us, doesn't it? 14 divided by 2 is just going to give us 7. So we're going to have 7 times 1 over 6 times pi or 7/6 times pi. So our angle in radians, after we went through the math and reduced our fractions down, we found that our angle in radians is equal to 7/6 pi. All right, that's in radians. Now we have to convert it into degrees. Well, we conveniently know the formula for that, right? Just talked about it a second ago. Let's write everything down that we know now. We know our angle in radians is equal to 7 over 6 times pi. And we know the formula to convert radians into degrees is going to be, or rather is, our angle in radians times 180 divided by pi. This is equal to our angle in degrees. So now we can just pass everything through, right? You just go ahead and plug in 7/6 times pi into this formula. Cool, let's do that. So we're going to have 7 divided by 6 times pi times 180 over pi well, notice the pi's cancel, don't they? So we can rewrite this then as 7 over 6 times 180 180 is divisible by 6, so let's rewrite that fraction. So we're going to have 7 times 180 over 6. All I did was rewrite the fraction. (180) divided by 6, that is going to give us 30. So we have 7 times 30, or just 210. So our angle in degrees is 210 degrees. That's it. Having said that, it's 210 degrees, right? Did I draw the circle correctly? Well, we know that at 180 degrees, it would just be the half circle, right? And at 270 degrees, it would be 3/4 of a circle. So it's somewhere in between what I drew up here on the board, which makes sense because 210 is somewhere in between 180 and 270. So yeah, this is about right, approximately. Cool, let's move on. To quickly wrap up this first lecture, let's talk about arc length, angular speed, and linear speed. Begin, arc length. We already know from the very beginning of the lecture how to calculate the angle in radians using both the arc length and the radius. To find the angle in radians, we said the angle in radians is equal to the arc length divided by the radius. Okay, well if that's the case and we now want to go in the other direction and find the arc length, then all we need to do is solve for s, right? So we multiply both sides by r, by radius. We find that arc length can be found using the formula s for arc length, is equal to radius times the angle in radians. Cool. That's all she wrote. That's all there really is to that. All right. Well, what about angular speed? Well, really, all angular speed is how fast you're rotating. Angles, speed. Okay, seems obvious, right? Well, here's the catch. Typically, when talking about angular speed, we like to keep things in radians. And for most of this class, we're going to want to keep things in radians. I should let y'all know that. So get used to thinking about things in terms of radians. But also get used to thinking about how radians and degrees relate to one another. Cool. Getting back to this stuff. So angular speed is going to be the number of radians rotated per unit time. And linear speed Well, linear speed is just going to be the arc length traveled per unit time. But hey, we just said arc length can be calculated using this formula above, r times the number of radians. So if we rewrite linear speed using r times the degree or the angle in radians, all divided by time, well, hey, we can rewrite that to be r times the fraction, our degree in radians, our angle in radians divided by time. Well, that fraction, that's angular speed. So we can rewrite linear speed in the form radius times angular speed. So we have two different equations. We actually have three different equations that we can be using. So let's look at an example then using this stuff. In this example, we have a clock. This is a clock. Don't you just love my artwork? The only correct answer to that question is yes. To say otherwise, instant F in the class, promise. Just kidding. All right, so we have this clock, and we want to know how fast the end of our second hand is going to be moving. So we want to know what the linear speed is at the end of our second hand. First thing we need to know, how long is that hand? Well, it's 10.2 centimeters. Okay. Well, if that's the case, I know that this second hand is moving with an angular speed of 2 pi radians every 60 seconds. Writing that down. We've got 2 pi divided by 60. So with this in mind, we know the radius and we know the angular speed. We want to know the linear speed. How fast the very end of this is moving. All right. Well, we know the formulas that we could possibly use to calculate linear speed. And based on the data that we have, we want to use this last formula. R times the angular speed. So let's put all this together. R times the angular speed. Well, we know R is equal to 10.2. Let's plug it in. And we know our angular speed is 2 pi times 60. Let's plug that in. 2 pi divided by 60. We can rewrite some of this. The easiest way to rewrite it would just be to multiply that 10.2 by 2. We're going to get 20.4 times pi all over 60. And without getting some ugly numbers, this is where I'm going to leave it at, because this is, for all intents and purposes, as reduced as what we needed in this particular example. Having said this example is actually in the lecture notes. However, the lecture notes take a slightly different route than what I did. So I want y'all to look at not just this lecture here, but also the notes. I'm going to do this continuously through the class where I might find an example in the lecture notes as I wrote them up originally and approach them slightly differently in the video, just to kind of give y'all a taste for the different approaches you might be able to take. Having said all that is all I've got for y'all today. If you have any questions, by all means, please shoot me an email, drop by during office hours. Like I said in the announcement before, I plan on having those figured out by Tuesday. It may be later than that, it may be earlier than that, but I plan on having them figured out no later than Tuesday night. Having said all of this, have a good one, guys.